In this program, we are going to look at today's in thing, sports. This means we'll be discussing physiology, training, and doping. Muscular bodies are all the rage. Wherever you turn, the advantages of physical activity are being praised on TV, in magazines, in doctors' offices. Being in shape does have many advantages. First, from a strictly biological point of view. You can find this out very quickly. Exercising does wonders for your eating habits and digestion. But there's more to it than that. A healthy mind and a healthy body. A good many people have managed to pull themselves out of a depression by throwing themselves into some demanding physical activity. But what does being in shape mean exactly? Before we answer that question, let's first see what happens when our body goes into action. Roughly 650 muscles stretch over our skeleton and coordinate our movements. A 70-kilo man has about 30 kilos of muscles. That is 40% of his weight. In women, the ratio is slightly less. The skeleton's muscles are called voluntary muscles, since they depend on will. Conversely, the heart is an involuntary muscle, since it contracts independently of our will. The same goes for the muscles in our intestines and blood vessels. A skeletal muscle, like the biceps, is made up of thousands of cells called muscular fibers. These fibers are exceptional in many ways. First, they have several nuclei, as opposed to only one for most other types of cells in the human body. Also, the fibers are extremely long, up to 30 centimeters in some muscles, whereas most cells are usually measured in microns, that is, in millionths of meters. So you need a microscope to see them. Each fiber can be compared to a cable made up of a multitude of thin parallel ropes, myofibrils. In turn, each myofibril is made up of innumerable parallel threads, myofilaments. There are two kinds of myofilaments: thick filaments composed of myosin protein and thin filaments composed of actin protein. When this bodybuilder decides to bend his arm, electric impulses go from his brain and down through his nerves. The nerve widens to form a motor plaque where it meets a group of muscular fibers. Inside the plaque, the impulse causes a chemical mediator to be released. The latter is picked up by the receptors on the fiber's surface. This triggers the sliding of the actin filaments against the myosin filaments. It's that sliding that constitutes a muscular contraction. The biceps shortens and the forearm bends. Despite months of training, the number of fibers in a bodybuilder's muscles does not increase. It's their volume that increases, and it can do so up to 50%. Its fuel is a large molecule rich in energy, adenosine triphosphate, or ATP. However, a relaxed muscle contains very little ATP, barely enough to work half a second. A body in action, therefore, has to fabricate ATP. To do so, it taps into three reserves of energy. At the start of a 100-meter race, or if a worker runs to catch his bus, the muscles have to react very quickly with maximum intensity. They draw from the first reserve, phosphocreatine molecules in the muscles. These are constantly transformed into ATP. It's the muscular spark plug. But the phosphocreatine reserve is small. At best, it enables the athlete to run his 100 meters, or our worker to keep going for a few seconds. If the effort is kept up, the body calls upon a second energy reserve, Glucose, a sugar present in muscles and blood. But there's a catch. A great deal of oxygen is required to transform glucose into ATP, 20 to 60 times more than when at rest. When our heartbeat speeds up and we pant for breath, it's to send additional oxygen to our muscles. However, it takes a full minute for the fresh oxygen to get to the muscles. Meanwhile, the incomplete degradation of the glucose produces lactic acid, a substance that slows down the chemical reactions in the muscles, bringing on a feeling of fatigue. Finally, the oxygen reaches the muscles. The glucose is almost completely converted into ATP. This results in water and carbon dioxide, easily eliminated by the body. The oxygen also enables the body to produce ATP from a third source, the fats stored in the body. A constant supply of oxygen thus enables an athlete functioning at roughly 75% of his maximum capacity to run, swim, or pedal for hours. A muscle's fibers are not all identical. There are two kinds. The slow contracting fibers, which function best in the presence of oxygen, and fast contracting fibers, which are more effective in the absence of oxygen. The proportion of these two types of fibers varies greatly from one individual to the next. That's why some people make excellent marathon runners, because their muscles contain a major proportion of slow contracting fibers, whereas others excel in sprint running, their muscles having a greater concentration of fast contracting fibers. In recent years, athletes have been breaking Olympic records right, left, and center. How can we explain the fact that they are suddenly stronger, faster, and better than their predecessors? One of the main reasons for this sudden improvement is that the training of athletes has become a real science. Today, each discipline has its own training techniques. That's probably why so many sports medicine experts proudly assert that it is scientific research that enables today's winners to outdo yesterday's. The days are long gone when an athlete's training depended solely on the trainer. Today, scientists work hand in hand with trainers, and the athletes benefit from the most recent findings in nutrition, physiology, biomechanics, and psychology. This athlete is working with physiologists specialized in exertion. They're assessing his maximum oxygen consumption, or VO2 max. That is, his capacity to use the oxygen in the air. In marathon runners and other sustained exertion specialists, VO2 max is the key factor of performance. Muscles need oxygen to be able to tap the body's reserves of energy. While the athlete runs, a pipe collects the air he exhales and transmits it to a computer that analyzes it. The more inclined the treadmill, the harder the athlete works, and the more oxygen he consumes, but up to a limit. Even if the treadmill is more inclined, the athlete is incapable of using more oxygen. He has reached his VO2 max. A sedentary person consumes approximately 45 milliliters of oxygen per minute per kilo. Years of training can bring the VO2 max of a marathoner to 80 milliliters a minute. Together with the measuring of his VO2 max, a few drops of the athlete's blood is regularly taken. The analysis shows the level of lactic acid in the athlete's blood, lactic acid being a substance produced by the working muscles. When the athlete first strains, his lactic acid level rises, then stabilizes. His muscles recycle the lactic acid they produce into fuel. His lactic acid level suddenly shoots up. The athlete is working almost at maximum capacity. At this level of exertion, the oxygen he is getting is no longer sufficient to fuel the efforts his muscles are demanding. More lactic acid is produced. It accumulates and slows down the chemical reactions in the muscles. Fatigue sets in. When competing, athletes try to stay just under that threshold to avoid wearing themselves out. When in training, however, they will try to extend the threshold to improve their performance. Another method used in training athletes is electrostimulation. An electrode is fastened to each end of the muscle that wants reinforcing. Electrical impulses make the muscle contract without the intervention of the brain. Weak electrical currents have been used for a long time in medicine to keep a modicum of strength in muscles of fractured limbs. The Soviets were the first to hook their athletes up to stronger currents from 100 to 150 volts. At this intensity, virtually all of a muscle's fibers will contract. Whereas with weight training, the weaker impulses produced by the brain only make some of the fibers contract. Electrostimulation thus enables an athlete to use 100% of his muscle potential. However, this technique is not without risk. Too strong a current can tear the muscle. Increasing VO2 max and muscular strength is not, however, enough to make a champion. Athletes must also perform their movements with optimum efficiency. This is where biomechanics comes in. Biomechanics is the analysis of movements in terms of the laws of physics. An ultra-fast camera films the athlete as he runs. The images are then projected one by one on a graphic tablet. For every shot, the operator presses on the points matching the articulations. The computer then registers the position of the various parts of the body at every stage of running. It can then break down the runner's performance, position of the trunk and arms, length of stride, speed, etc. Thanks to biomechanics, experts can now determine if a pole vaulter takes off at a perfect angle, or they can evaluate a diver's performance. Skiers also have to contend with the laws of physics. Bad posture will increase air resistance and slow the athlete down. That's why for the past 20 years, wind tunnel work has been part of a professional skier's training. The skis are fastened to a sophisticated scale, which measures the resistance offered by the skier's body. This enables the experts to determine the most aerodynamic position. It was wind tunnel testing, for instance, that helped develop the so-called egg position used by downhill skiers. Trunk parallel to the ground, forearms placed in front of the body, and elbows inside. And it's also in wind tunnels that the resistance of the skier's clothes is tested. Nutritionists and psychologists round out the team that works with an athlete. The nutritionists prepare diets specifically for each discipline. The psychologists help the athletes overcome stress and think like champions. In Olympic competitions, the difference between the winner and the loser has little to do with physical shape. It has much more to do with mental attitude. Believe it. Thanks to mental imagery techniques, athletes now learn to visualize themselves as winners. Me on the top step of the podium. Me on the cover of Time magazine. Their fixation with being the best in the world, ambition turned obsession, is probably what has caused some athletes to abuse themselves as they have. Of course, I'm referring to drugs. Doping has always existed, and even if we have started to strip some athletes of their medals, the problem is far from solved. Whether amateur or professional, in their desire to make it to the top step of the podium, athletes are tempted to resort to taking various substances. The substances are generally broken down into 5 groups. Beta blockers, drugs used mostly to regulate the heartbeat. Marksmen who press the trigger between 2 heartbeats use it to slow their heartbeat down and reduce their trembling. Diuretics increase the discharge of urine. Greater passing of urine dilutes the presence of forbidden substances. Indeed, urinalysis reveals whether an athlete is taking drugs or not. Narcotics, like morphine, enable an injured athlete to block out his pain and therefore to compete. The whole range of uppers, including amphetamines, cocaine, and antidepressants, these drugs conceal the sensation of fatigue and drowsiness, kill pain, and boost self-confidence. Until the mid-60s, amphetamines were the drug most commonly used by athletes. But the effect of these substances is short-lived. This means they have to be taken only a few hours prior to competition and are therefore easy to detect. For that reason, they are seldom used nowadays. Synthetic hormones have taken their place, with its star player anabolic steroids. Steroids are synthetic molecules, that is, molecules made in a laboratory, and are similar to testosterone, a male sex hormone produced in the testes. At puberty, testosterone is what changes a boy into a man. Growth of body hair, voice change, increase in muscular mass. It's because testosterone is present in greater quantities in young males than in young females that the former develop a more sizable musculature. Substances such as testosterone, which increase muscle size and strength, are referred to as anabolic. Artificial copies of testosterone have been fabricated for over 50 years. Steroids were first used on survivors of concentration camps, then on accident and burn victims, and even children considered too frail. They were thought to have regenerating qualities. Nowadays, doctors will only prescribe them as a last resort when no other remedy is available, because the side effects of steroids can be fearsome. It was during the 1960s that athletes, wanting to increase their muscular strength, discovered steroids. Steroids promote the synthesis of proteins, the blocks that make up muscular fibers. To be effective, steroid treatment should be combined with intensive weight training and a high-protein diet. When administered in this way, steroids increase the volume of muscular fibers. Steroids enable athletes to train for longer periods of time and more often, and help repair any muscular fibers that have been damaged through exercise. They therefore bring on a feeling of well-being and make athletes more competitive, urging them to surpass themselves. Steroids enable athletes to increase their strength much more quickly than weight training alone. Hence the term muscle fertilizer. Steroids are virtually undetectable if the athlete stops taking them a few weeks before competing. Over the years, laboratories have learned how to reduce the side effects steroids have of emphasizing masculine characteristics in users and yet maintain their anabolic power. Nonetheless, steroids still produce very visible side effects. A man's body will reduce its own production of testosterone and take on feminine characteristics, such as breast development, shrinking of the testes, decrease in sexual drive. In women, the reverse is true. They tend to develop more masculine features, greater pilosity, deeper voice, shrinking of the ovaries. But the effects can be more serious: lesions of the liver, cancer of the prostate, and behavioral disorders that can reach the point of paranoia. And though the muscles become stronger, the tendons fastening them to the bones do not, which can lead to frequent injuries. In recent years, a new hormone has made its appearance in gyms and stadiums, the synthetic growth hormone. Like steroids, the growth hormone promotes muscle development at the cost of very unpleasant side effects: hypertrophy of the hands, feet, and nose, and metabolic disorders. how far will they go? Genetic engineering will soon create new molecules that will push the limits of human performance even further. And up until now, history has shown that the anti-doping squads are always a few steps behind the pharmacopoeia of athletes. Has this made you want to exercise? Yes, I know, there's always a good excuse. Jogging in the city isn't the healthiest, and no one wants to jump in a pool and get an earache. Maybe you're right. Go for a walk. It may not seem like much, but it's excellent exercise.